Hi everyone, sorry about the delay. My internet isn't working. I just got it to start working again. I have to reboot the router. It looks like my internet's working now. That's good. I was about to send all of you a Blackboard email, but the internet's back on, so we're good. That's good. Okay, so let's give a minute for everyone to join, and then we can start. All right, good. So my internet is working. That's good. Good morning. Okay, so again, sorry about that. My internet stopped working for a little bit. I had to restart my router, but it looks like it's working again, so that's good. Okay, so I'm going to share my screen. Okay, so you should all see Word now on the screen. Wait a little bit longer. Make sure everyone gets here. Okay. All right, so you should see the homework on the screen. Okay, good. Okay, so homework 2 was due today. So does anyone have any questions about homework 2? Anyone have any questions? Okay, so for instance, in homework 2, 1.4.5, number 4, it says a card is drawn at random from a standard deck of 52 playing cards. So that each card has an equal probability of being drawn. Find the probability of drawing each of the following. So, let's say, for instance, it's for A, the probability of a black queen, right? So the probability of a black queen, right? I'm just going to denote it as BQ, probability of a black queen. That's equal to the number of black queens, right, divided by the total number of elements in the set. And so I usually use a lowercase n. So we use a lowercase n here and capital N here. So the number of black queens, right, there are 4 queens, but only 2 of them are black. And that's out of the total 52 in the deck. So 2 over 52 or 1 over 26 is the odds of a black queen, right? That's A, right? And then if we look at the probability of a black ace or a red queen, right? The probability of a black ace or a red queen, that's this, right? So I'm just going to put that there, that event. Then how many black aces are there or red queens? Well, black aces and red queens, they're mutually disjoint, right? There's only 2 black aces and there's 2 red queens, no intersection between them. So there's a total of 4 black aces or red queens out of the total 52 in the deck, and that's the same as 1 over 13. Okay, so that's A and D from number 4. All right, so hopefully that makes sense. Okay, good. Any questions about the homework? Okay. 2.22a. Okay, 2.22a. Consider the experiments A, B of exercise 1. Okay, that's this exercise. Okay, find the probability that the position of catcher, pitcher, first baseman, and second baseman will be filled by Jackson, Williams, Gonzalez, and Jacobs, respectively, in experiment 1A. Okay. So there's a group of 15 baseball players, right? So there's a group of 15 baseball players, and we want to find the probability that the position of catcher, pitcher, first baseman, and second baseman will be filled by Jackson, Williams, Gonzalez, and Jacobs, respectively. That's the event, right? So we want the number of ways that can happen divided by the total number of ways to fill these positions, right? So there's 4 positions, 1, 2, 3, 4. But the order matters because the first one is going to be catcher, the second one's going to be pitcher, and so forth. So what we have here is we have 4 permutations, right? Of a set with 15 elements in it. There's 15 players, and we want to order 4 of them. So that denominator is 15p4. Now the numerator is just the number of ways of choosing a catcher, pitcher, first base, second baseman with Jackson, Williams, Gonzalez, and Jacobs, respectively. There's only one way to do that. So the probability is 1 over 15p4. That's 1 over 15 times 14 times 13 times 12. Does that make sense? You're welcome. Okay, right. So, right. So the number of elements in that sample space is you do fill the positions of catcher, pitcher, first baseman, and second baseman out of the 15 people. That means you have 4 orderings of 15 people. And so how many of the 4 permutations in a set with 15 elements are there with that one specific choice? Well, 4 people is 1. So 1 out of that. All right. So that's number 2, 2A. Okay. Okay, and so I put the video up online. So the things I wrote down will be on the video, right? The way I presented them here. Any other questions about homework 2? 5A. Okay, so 5A Okay, so 5A, it says, in the simultaneous rolling of a green die and red die, assume that all 36 possible simple outcomes are equally likely. Find the probabilities of the following events. So A is a sum of 7. Okay, well, so you have a red die and a green die, right? So the red die is going to be green. Okay, so there's going to be green and red. So the green die, the result is going to be in the first coordinate. And in the red die, the result is going to be in the second coordinate. So that's what the meaning of the ordered tuple is going to assign an order so that we can differentiate between the outcome of the red die and the result of the green die and red die when we rolled. Okay. So find the probabilities of the following events. A sum of 7, because you said 5A. Okay. So in order to find the probability of, let me choose a completely different color. Let me choose purple. This is 5A. So in order to find the probability of a sum of 7, right? The sum equals 7. The probability of the sum equals 7. You want to find the number of elements, the number of ways you can get a sum of 7 divided by the total number of 36 rolls, right? So also it tells you right there, when you roll a green die and a red die, at 6 times 6, 36 ways to roll 2 dice, right? And so how many of those 36 rolls is there a sum of 7? Well, you could have 1 plus 6. You have 2 plus 5. You could have, this is ordered pairs. So you have a 1, then a 6, 2, then a 5, 3, then a 4, 4, then a 3, 5, then a 2, and then a 6, then a 1. Okay, so you have 6 possible ways to get a sum of 7. So that's 6 over 36, which is 1 over 6. As a decimal, that's 0.1666, and so forth. Okay, a decimal point there. As a fraction, it's 1/6. Does that make sense? So the probability of a sum of 7 is the number of rolls of 2 dice where the sum is 7. That's just counting. You can count the number of simple outcomes where the sum is 7, and this is a total of 6 of them. 1, 2, 3, 4, 5, 6, and then it's a total of 36 rolls. 6 over 36. Okay, does that make sense? So that is that's 5A. Number 3. Says a sample space S consists of 25 equally probable sample points. If n sub A is 10, n sub B is 15, n sub C is 8, n sub AB is 5, n sub AC is 3, n sub BC is 5, n sub ABC is 1. Find these probabilities. Okay, so again, I'm going to erase this. I'm writing on the screen on the homework assignment because I think that if you have the problem in front of you while I'm doing it, that'll make sense. And when you open the video, you can pause it. So if you want to look at the work I did, you can pause it at the point at which I was going over that problem. Okay, so I'm going to choose a different color now. So I'm going to choose pink. So okay, so we're doing. Is it this one? No, you said number 3. So there's 2 number 3s. I'm assuming you mean 1.4.5 number 3. Is that right, Aima? This one, right? The one I have circled? Yeah, okay, good. Okay, so 25 equally probable outcomes. Okay, so you have a set A. You have a set A. You have a set B. And you have a set C. So A, B, and C. This is the universal set. N sub A is 10. And so actually the main thing I want to point out is this. So oftentimes you want to work backwards in life. And so here they're giving you the intersection of all 3 sets that there's 1 element in it. So let's start from the inside out. You have 1 in the intersection. Now for NBC equals 5, that means there's a total of 5 in the intersection of B and C. There's already 1 here. So in order to be a total of 5, there needs to be a 4 there. So I'm going to pause for just a second. And I want you to see these 2 things I just did, right? The intersection of all 3 sets has 1 element in it. And the intersection of B and C has a total of 5. Since we already counted for 1 of them here, there has to be another 4 that's in the intersection of B and C and not in A. Does that make sense? Right? So you need to understand those steps in order to understand the rest of it. The rest of it is just basically off of that. So if that makes sense, then the rest of it can be easy. Yeah, so you work from the inside out. So now A and C, the number in A and C is 3. And so if there's 1 here, there has to be 2 more here. So 2 plus 1 is the 3 there. The number in A and B is 5. So if there's 1 here, there has to be 4 here. So that 1 plus 4 is 5. Then the number in C is 8. And so if there's a total of 8 and C, we already counted for 7 of them here. So there's only 1 more that can go here. And then if there's 15 in B, there's already 4 plus 1 plus 4. There's already 9 here. Just be 6 more here so that they add up to 15. And if the total in set A is 10, this 4 plus 1 plus 2 is 7. And so it has to be 3 more in only A and not B or C. And so that's the Venn diagram. Okay. Now, oh wait, and then it says there's a total of 25. There's a total of 25 equally probable sample points. And so let's add up the number we have so far. We have 3 plus 4, which is 7, plus 6, which is 13, plus 2 is 15, plus 1 is 16, plus 4 is 20, plus 1 is 21. There's a total of 21 in at least one of these 3 sets. There has to be 4 more that are in none of the 3 sets. There's another 4 that's in the complement. That's outside of those 3 sets. And so now all the numbers add up to 25. And so if you want to find the probability of A, let's say, the probability of A, right, is equal to the number of elements in the event A divided by the total number of elements in the universal set. When the number in A is 10 divided by the total 25 that are in the universal set. That's the same as 0.4 as a decimal, because that's 40 over 100. It's 0.4, right? Now, the probability, so what we did here was we did the probability of A. The probability of AB prime, the probability of AB prime would be the number of elements in the set AB prime divided by the total number of elements in the set. And so the number of elements in AB prime, they're in A and not in B. So the elements that are in A and not in B has to be in A and not in B. So you see that this is the part of A that's not in the circle B. So 3 plus 2 is 5. There's a total of 5 elements in A and not in B. So there's a total of 5 out of the total 25. So that's 1/5, which is 0.2. Okay, so 0.2 is the probability of the event AB prime. Okay, and you can just continue there. Let me do the last one. Probability of not A and not B. So the probability of not A and not B, well, so I'll answer that question is, okay, so you said, wouldn't we include the value of 1 in C and 4 outside the circle? So I don't know what you mean. Do you mean the 1 here that I'm pointing to? For which problem are you talking about? Which problem? Well, no, oh, no, so you mean for AB prime, right? But AB prime means it's in set A and not in B, right? It has to be in the blue circle. It has to be in the circle A. See circle A? Here's set A, right? It has to be, it's AB prime, right? So AB prime means that you're only considering elements that are in A, right? See the A here? See the A here, right? That means it has to be in A and not in B. And so it has to be in the circle A and not in B. So you see how the yellow section are the only sections in circle A and not in B? Does that make sense? Okay, good. So, okay, so that makes sense. Good. And just probably of A prime B prime, right? That means it's not in A and not in B. Well, so A prime B prime, right? A prime, that's A prime B prime. Well, almost. So this 1 is not in A and not in B, and the 4 also isn't. Don't forget the 1 is also not in A, not in B. So my first thought was 4 also, but then I thought about it and I realized that if it's not in A and not in B, it could still be in C. So it's 5, right? So the probability of A prime B prime is 5 over 25. That makes sense? Which is 1/5 or 0.2 as a decimal. Hastine, does that make sense? Hastine Meliani Maida, I'm sorry if I'm mispronouncing your name. You said, is it 4? So you get it's 5, right? Okay. So A prime B, right? Well, okay, so Aima, if I'm pronouncing right, you tell me, what is the probability of A prime B? What is the probability that it's not in circle A, but is in circle B? Aima, I want Aima to answer. It's a probability, right? So it has to be 10 divided. Yep, good. So there's 10 sample points in the event divided by the total number of sample points in the universal set. So it's 10 over 25. Very good. That's it. So that's all of 3. It's A, B, C, and D for number 3. You're welcome. Okay, good. So, okay, it's better if you participate out loud than through the chat. But if I can see the chat, if Zoom lets me, I can look at it from time to time. As a human being, I can't do a million things at once. I'm not an octopus, but I have one brain. But I'll try to just look at the chat while I'm also doing something else. Okay, so okay, so we have. Okay, so that's good. I think we covered homework 2 very well. Okay, so this class I want to talk about Bayes' theorem and other theorems on conditional probabilities. Okay. So our first section is going to be that, and that's going to take some time. If there's time, which is probably will be, we're also going to talk about independent events. Okay, definition of an independent event, and theorems. Okay, and that will probably be, and then if there's time, there's going to be examples. Okay, good. Okay, so let's get started. Give me 1 second. Alexa, stop. Alexa, stop. Sorry about that. My Alexa was acting up because my internet wasn't working, so it then turned back on again, and the alarm went off. I couldn't turn it off earlier. Okay, so then let's get started. So for 3.2, we have Bayes' theorem, Bayes and other theorems on conditional probability. Okay, so we have theorem 3.1, which is the probability of A prime given B is equal to 1 minus the probability of A given B. Okay, so this is one theorem, theorem 3.1, and so the theorem says the probability that of the event A prime given B is equal 1 minus the probability of A given B. So let's look at an illustration of this on the whiteboard. Okay, so the theorem I just wrote down, that's what I want to show. So I want to illustrate how the probability of A prime given B is equal to 1 minus the probability of A given B. Okay, that's a minus. Okay, so the probability of A prime given B is equal to 1 minus probability of A given B. So if you have your set A and you have your sets B, here's the universal sets. And so the region A prime given B, right? A prime is what's not in the circle A. So the region here that we're looking at is here. So if it's not in A prime, right, it means it's not in circle A. So we're looking at this region, right? This region is A prime. This region is A prime B, right? Now the probability of A prime B is equal to the by the definition, A prime given B. Is equal to the probability of A prime and B divided by the probability of B. And so if you're looking at the number of elements in A prime B, which is this, the number of elements here, and you're dividing by the total number of elements in set B, right? So it's the It's the probability of the red part divided by the probability of the blue part. That's that conditional probability, right? And the probability of A given B, well, the probability of A given B is this amount. Let me draw it separately. So if you have the set A and you have the set B, now circles are smaller. So now the probability of A given B, so I'm looking at this guy. If you start with this, right, then the probability of A given B is equal to the probability of AB, which is that region there, divided by the probability of B, which is the entire region again, right? Now, the purple part here and the red part here, do you see how they add up to the entire set B? So what happens is that the probability of A prime given B plus the probability of A given B is equal to, well, if you add the red region here, the probability of the red region plus the probability of the purple region, you get the probability of B. And that's both, they're both divided by the probability of B. And you get equals to 1. So I showed us that this plus this equals 1, and therefore the probability of A prime given B is equal to 1 minus the probability of A given B. Does that make sense? And I tried to illustrate for you why it would make sense that this equation works, right? You're just basically finding the probability of the red region plus the probability of the purple region, and that's equal to the probability. And then, well, it's the probability of the red region plus the probability of the purple region, divided by the probability of B. So you end up with probability of B over B, which is 1. That's because the probability of A prime B plus the probability of AB is equal to the probability of B. Right? The probability of the red region plus the probability of the purple region is equal to the probability of the entire circle B, because they're disjoint, but together they're all of B. Make sense? Okay. So let me go back here. For the proof, I illustrated the proof on the whiteboard, and just to write it in words, to write it out. If you have the probability of A prime given B, these are just formulas though, right? So what you're seeing, the visualization is important because you're understanding why, what's really happening. You're understanding the math behind it, right? So the probability of A prime given B is probability of A prime B over probability of B. And so this is equal to the probability of B minus the probability of AB. That's still divided by the probability of B. This is equal to P of B divided by P of B minus P of AB divided by the probability of B. That's equal to 1 minus P of AB divided by P of B. That's 1 minus probability of A given B by definition. And so this is equal to that. All right, so again, this is equal to this because by definition, right? This is by definition of conditional probability that this is equal to that. The probability of A prime B is equal to the probability of B minus the probability of AB. Right? That's because A prime B is disjoint from AB, but their union is all of B. Okay, so I illustrated that in the picture. So probability of A prime B is equal to this minus this. then divide by b, you get p of b over b minus p of ab over b. That's 1 minus this. By the definition of conditional probability, this is equal to the probability of a given b. That's now you get that this is that, okay? But you might also want to see look at the picture I drew on the whiteboard to understand that. Okay. Okay, so theorem 3.2. So there's several parts. So the probability of AB is equal to P of A given B times P of B. And this is if the probability of B is positive. Okay, and also the probability P of AB is equal to the probability of A times probability of B given A. This is if the probability of A is positive. Yes, this is part A. Well, okay, so for this part, the probability of A given B, right? So I'm going to write proof of A here. It's proof of A. If you have the probability of, it's better to start with the weird side first and show it's equal to the not so weird side. So let's start with the right side because that one looks more stranger. So this is equal to P of AB divided by P of B by the definition of conditional probability. And now times that by P of B. The P of B's cancel and you get P of AB. See that? This is just by a definition of conditional probability that this is equal to this. And then you keep that the same, and then the P of B's cancel and you get that, right? And this is if P of B is positive since the proof needs a non-zero number in the denominator. Right? The argument uses the fact that you divide by P of B here, right? If P of B was equal to 0, then this wouldn't work because you can't divide by 0. But since it's positive, you're dividing by a non-zero number here, and then so this argument works. Okay, so that's A. That's the first equation, A. The second equation in A is almost exactly the same. If you take P of A times P of B given A, by definition of conditional probability, that's P of A times, well, P of BA is P of BA divided by, sorry, probably B given A is P of BA divided by P of A. The P of A is canceled and you get P of BA. And this is if probability of A is positive, right? And it's given here. All right, and that's because that's since you divide by P of A in the proof, right? In the proof, you divide by P of A, and so you need a positive P of A in order for this argument to hold that P of BA is equal to P of A times P of B given A. Okay, so that's the proof of part A of that theorem. Okay, so let me write out the full theorem, and then I can think of try to take an example. So P of ABC is equal to P of A times P of B given A, and then times P of C given AB. And this is if the probability of AB is positive. Okay, and then part C, you have the probability of A1, A2, A3, ... and AN. So this is the intersection of all those n elements, the probability of that is equal to P of A1 times P of A2 given A1 times the probability of A3 given A1, A2. Continue the pattern, and then the last one is P of A sub n given A sub 1, A sub 2, dot, 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 up to including A sub n minus 1. That's part C. And this is if the probability of A1, A2, dot, 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 A sub n minus 1 is positive. Well, so P of BA, right? Let me put a note here. P of BA is equal to the probability of AB, right? But the reason, so I get what you're saying. You're right. When you do the formula exactly the way it's written, that would technically be the way you would write it. I just wrote it this way because, that's the event AB. But technically, right, P of BA would, let me put this way, P of AB equals P of BA. And that would be equal to the probability, right, yeah, they're just equal. So right, so they're just equal. So you're right. Usually in a formula, you might fill in exactly. You might do that, but the point I want to illustrate here is that these two probabilities are exactly the same. That makes sense. So don't look at this in order to understand. In order to know the formula of conditional probability, you wouldn't think that, but you should already know the formula for conditional probability, and then recognize a second thing, that these two are actually, the same. P of BA and P of AB. Okay, so does that make sense? Okay, great. Okay, so that's A, B, and C, and so you want an example. One example. Okay, so for part A, you want the probability of A and B is equal to the probability of A given B times B. So let's look at the whiteboard here. So if you have the universal sets, that's the universal set, and then you have event A and you have event B. Right, and so what we're talking about is illustrating that the fact that the probability of AB is equal to the probability of A given B times the probability of B. And this is if the probability of B is positive. Okay. Okay, that's if the probability is positive. So the probability of A and B is right in the intersection of the two sets. And so if you look at A and B here, right, probability of A, B is just counting the number in the purple set divided by the number in the entire set. So the probability of A given B, this guy, right? That's just the probability of A and B divided by the probability of B, right? But now if you multiply that by P of B, it cancels and you get P of AB. So in both cases, you're just getting the number of elements in the purple region divided by the total number of elements in U, right? So examples, these equations hold, they always hold. And so you could take any example and it will work, right? So if I chose, okay, so if I chose 2, 1, 2, 1, okay, so it's 2 here, 1 here, 1 here. Then the probability of A and B would be 1 out of 6, right? Because there's one element out of the total 6 that are in A and B. Probability of A given B would be the probability of A and B, which is 1 out of 6, divided by the probability of B, which is 3 out of 6, times the probability of B, which is 3 out of 6. Right? So 1/6 is equal to 1/6 divided by 3, 6 times 3, 6. Do you see that example? Okay. So the other ones are just very similar. You could take any A and B you want, draw the Venn diagram correctly, find the probabilities, and you'd see that they would cancel. So that would be an example of all of them. You would just repeat that same idea. So you can write a Venn diagram, put in a certain number of elements in each subsection, and then find the probabilities, plug in, and you'll see that the formula holds. And so that would be how to make the example for each one. Okay. Okay, so that's theorem 3.2. And so C is a little weird, but for C, it's just like A. It's just like A. If you wanted to prove C, and you would just see that this whole thing here, this entire expression here, this is equal to well, so you have the probability of A1, but then times the P of A2 given A1 is P of A1 A2 divided by P of A1. Right? That would be this thing. Right? It's P of A1 A2 divided by P of A1. I'm just putting it in the order. I'm ignoring the order from the formula. I'm putting it in just left to right order. It would technically, if you follow the formula exactly, it would be A2 A1 over A1, right? Probably A2 A1 over probably A1. I'm just making the order so that it's in order A1 A2. Now next, right? So for probabilities, it doesn't matter the order of the events if you're intersecting them, right? So this is A1, A2, and A3, probability of that, divided by the probability of A1, A2. Okay, so maybe you can see the pattern now already. These terms are canceling. But then you keep going. You keep going with this product until you reach the last one, which is the probability of all the events, intersection of all the events, A1, A2, ... A sub n minus 1. Actually, and A sub n, because you have that, and then divided by, and then this is the probability of the intersection of A1, A2, but only for the conditional parts. This is A sub n. This is A sub n minus 1. Okay, so now you have this. So that product is equal to this product. But look, the terms will cancel. This numerator cancels with this denominator, right? And this numerator will cancel with the next denominator. If we did the next term here, if we did the next term here, it would be the probability of A1, A2, A3, A4 divided by P of A1, A2, A3, right? And if we did the term before this one, it would be P of A1, A2, dot, 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 A sub n minus 1. And this would be P of A1, A2, dot, 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 A sub, and it would actually end at the one before it. It would be n minus 2 here. Okay, and so I just added a few more terms. So you can see this cancels with this cancels with this would cancel with the next one, dot, dot, dot. This would cancel with this would cancel with this. So all the terms would cancel except for this term, for two terms, this term and this term. See how there's a diagonal right cancellation? It's the only thing left would be that term and this term. The two blue terms are the only ones left that would not cancel in this product. But then here you have P of A1, right? So you have a P of A1 here. So this is also left. So after you cancel all the black terms, you have this term, and you have this term from the beginning. So the P of A1s cancel, and now you're only left with that term. So now you're only left with the probability of A1, A2, dot, 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 A sub n. And that's what C says. It says the probability of that is equal to this product, is equal to this product, right? So what we show is that this thing, which is this, is equal to this, right? And that's if P of the intersection of these events is positive. If the probability of the intersection of these sets is positive, that means this is positive. But also, what that also means is that, note that by assuming that the probability of the intersection of all n minus 1 of those sets is positive, we are assuming that all the denominators, all the denominator probabilities in the proof of part C are positive, right? If the probability of all of these events happening is positive, that means that the probability of any of these events is positive. That means the probability of A1 is positive. That means the probability of A1 and A2 is positive. It means the probability of this is positive and this is positive, okay? And so we can deduce from that one assumption that P of A1 is positive, that P of A1 is positive, that P of A1 comma A2 is positive, that the probability of A1, A2, and A3 is positive, and so forth, up to including P of A1, A2, dot, 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 A sub. And we already have up to n minus 1. So I'm just going to continue this to n minus 2 is positive. And so we also know that up to n minus 1 is positive. So all the denominators are positive, probabilities are positive, and so we can divide by them, and so the proof works. Okay, so note, we only need to show that this, if you know that this one probability is positive, then all of these denominator probabilities are positive, because this set is a subset of each of these sets. The circle, the intersection of these n minus 1 sets is contained in just one set. It's contained in the intersection of only two. It's contained in the intersection of only 3, right? So like in a Venn diagram illustration, if you had the intersection of 3 sets, right? And let's use pink for it. The intersection of these 3 sets, this is A1, let's say A2, A3, but there's even more than 3 in the problem. A1 intersection A2 intersection A3 is a subset. That pink region is a subset of, let's say, the intersection of A1 and A2, right? So this region is the pink region, right? But then if you have, let's say, green, if you have the intersection of A1 and A2, right, the pink region is a subset of the green region, right? So A1, A2, A3 is a subset of A1, A2. And so the probability of the pink region is positive. That means the probability of the green region is at least the probability of the pink one, which means the probability of the green event is also positive. So you do need to know proofs, right? Now, will it be in a test? You know, I'm not going to say, but in terms of understanding mathematics, you need to know proofs, right? The point of mathematics is to write proofs. That's the entire point of mathematics. Okay. Okay, let's do an example. So example 3.5. So suppose 60% of adults over 30 are college graduates. Okay, further, suppose 80% of college graduates over 30 have incomes over $15,000. A, if a college graduate over 30 is selected at random from the community, what is the probability he or she has an income of $15,000 or less? So for this, I'm going to move this to the next page. That way we have plenty of space. So suppose 60% of adults over 30 are college graduates. Further, suppose 80% of college graduates over 30 have incomes over 15,000. If a college graduate over 30 is selected random from the community, what is the probability he or she has an income of $15,000 or less? Okay, so maybe write this down or have, right? So I want to go to the whiteboard. And so, right, this is going to leave the screen. Let me see if I can paste this on the whiteboard. Let me see if I do paste, if it'll let me just. All right, yeah, that works. Okay, so here's the problem, right? Suppose 60% of adults over 30 are college graduates, okay? So a college graduate over 30, that's everybody, right? So we can think of the universal set as being a college graduate over 30, right? Over 30 as a college graduate. Oh, sorry, over 30 is going to be the set, not whether or not they're college graduates, right? So there could be college graduates, there could be not college graduates. So the over 30 part is going to be the universal set. So now college graduates, right? That's a set of its own. So these are college graduates, okay? So college graduates. So I'm just gonna label college graduates as college. That means college graduates. That's 60% of the entire universal set. Further, suppose 80% of college graduates, 80% of the people in the circle over 30 have incomes over 15,000. Okay, so now we're talking about another event that have incomes over 15,000. Okay, so let's introduce another set. And let's say this set is income over, so income greater than 15,000. Okay, so we have people over 30, and we have people that are college graduates over 30, and we have people who are not college graduates over 30. We have people over 30, still over 30, right? We have people over 30 that have incomes over $15,000. And we have people who are college graduates with incomes over $15,000 who are over 30. And then we have people either, right? So these are our sets here. So A is if a college graduate over 30, meaning in the red circle, is selected at random from the community, what is the probability he or she has an income of $15,000 or less? And so the region that we want is this region here. We're looking at what is the probability he or she has an income, what is the probability he or she has an income of 15,000 or less? Well, so an income of 15,000 or less would be, this is a college graduate over 30, right? The assumption is that you have a college graduate over 30. So assuming you have a college graduate over 30, you're looking at, when the income is 15,000 or less. So we're looking at this orange region. Okay. But when you're doing conditional probability, you have to, so let's do this. Probability of so I'm going to introduce names. So I'm going to make O equal to over 30, the event over 30. Oh, actually, that's the universal set. So it is that, but oh, good. Oh. Okay, there's going to be scribble marks there. Okay, so then for the red, the college graduates one, right? So let's call this C. This is going to be college graduates. So I'm going to write college here. So event C is the event someone's a college graduate. And then the pink one is going to be, I'm going to call it I. And this is for incomes greater than 15,000. Okay, and so what we want is the probability if a college graduate over 30 is selected at random from the community. So if a college graduate, so the if part tells you the assumption, right? So if a college graduate, so we're assuming the person's a college graduate, and we want to find the probability has an income of 15,000 or less. And so it's not I, it's I prime. It's the complement of I. Person does not have an income over 15,000, has an income of 15,000 or less. So you want the probability of I prime given C. This is equal to right? So this is equal to the probability of I prime C divided by the probability of C. The probability that someone does not make more than 15,000 and is a college graduate divided by the probability of a college graduate. Okay, the assumptions in the problem. Suppose 60% of adults over 30 are college graduates. That tells you that the probability of a college graduate is 0.6 or 0.60, right? 60% of adults, suppose 60% of adults over 30 are college graduates. So the probability of C is 0.60. So suppose 80% of college graduates over 30 have incomes over 15,000. That's telling you that the probability of a college graduate who's over 30 has an income of over 15,000. The probability of CI is equal to 0.80. Okay, so CI would be like this region. So this 0.80 would be like in here in the intersection, right? So the probability that someone's a college graduate and has an income of over 15,000 plus the probability someone's a college graduate and does not have an income of over 15,000 is equal to the probability of a college graduate. The probability that you're in this region, the probability you're in the intersection of C and I, plus the probability you're in, plus the probability that you're in C and not in I, that's this guy, right? So the probability that you're in this region plus the probability you're in that region is equal to the probability of the red circle, P of C. And so P of CI we see is 0.80 plus the probability of CI prime is equal to the probability of C, which is suppose 80% of college graduates over 30 suppose 80% of college graduates over 30 have incomes over 15,000. 80% of college graduates over 30. So 0.60 is the odds of someone being a college graduate. 80% of that has incomes over 15,000. So P of CI is 0.80 times 0.60. That's equal to the probability of C, which is 0.60. Okay, so probability of CI plus the probability of CI prime is equal to the probability of C. Probability of this part of the red circle plus that part of the red circle is equal to the probability of the entire red circle. Probability of CI is the probability that you're a college graduate over 30, which is 0.60, and also income over 15,000. I'm sorry, no, not that. 80% of college graduates over 30. So 80% of the 60% have incomes over 15,000. Okay, so probability of college graduate and is this. And so now you just solve for P of CI prime. So the probability of CI prime, which is the same as I prime C, is equal to 0.60 minus that. Okay, and so 0.60 minus that is then equal to 0.12. Okay, so you have 0.12 divided by the probability of C, which is 0.60. And so this is 1/5. 12 divided by 60 is 1/5. 0.12 divided by 0.60 is 1/5. And that's equal to 0.2. Okay, so again, the probability of C and I, the probability of this region, plus the probability of CI prime, this region, they add up to the probability of C. And since this probability is this plus this equals this probability, you solve for this one, and that's 0.60 minus 0.6 times 0.8 is 1.12. And so you plug it in here, divide by that, and you get 0.2. So I didn't. So I did it. I did it this way. There's another way to do it, right? So there's another way. So okay. So on the whiteboard, I illustrated the solution. Right? So I illustrated so you can see it. But if you want to use that formula, okay. So if you want to use that formula. Then what you want is the probability of if, what's the probability of that? You want the probability of I prime given C, right? That's equal to 1 minus the probability of I given C, right? So if you use the formulas, you get 1 minus, and then, okay, and so then the probability of an income over 15,000 given as a college graduate, right? So 80% of college graduates over 30 have incomes over 15,000, and so that's this guy right here. Because you're given that it's a college graduate over 30, and so 80% of college graduates over 30 have incomes over 15,000, and so that's the 0.80 there, and so 1 minus 0.80 is 0.20. Okay, and so that's the answer, a faster way. But with the Venn diagram, I'm illustrating for you how how you get the answer. Okay, so part B, what percent of adults over 30 in the community are college graduates and have incomes over 15,000. Do you mean in A, Keyshawn? So in A, I subtract, right? Okay, so oh, in B, yeah, you do multiply. So right, so what percent of adults over 30 in the community are college graduates and have incomes over 15,000. So college graduates is C, and incomes over 15,000, I said, was I. This is the probability of CI. Well, that's equal to the probability of CI. This is the probability of C given I so probability of I given C times the probability of C. Okay, but the probability of I given C we already saw was 0.80. And then the probability of C we know is 6.60 because suppose 60% of adults over 30 are college graduates. That's 0.60. That's the number I was looking at earlier. That's 0.48. Okay, and so yeah, so you multiply these two probabilities to get that one in B. Okay, good. Okay, so that's example 3.5. So let's look at another theorem. Theorem 3.3. Let capital S be a sample space if B1, B2, Bn are mutually exclusive events such that S is equal to the union of these events. And the probability of B sub I is positive for all those I. Then for any event capital A of S, part A is that the probability of A is equal to probability of A B1 plus the probability of A B2 plus, we're basically using this for two sets. Probability of A Bn is just applied to more sets, A Bn, and you also have part B, that P of A is equal to P of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2. So this might look hard, but it's directly from A. So first you would think of prove A, and then you would prove B. This is plus plus probably adding up all the ones in between, probably of A given B sub n times the probability of B sub n. Okay, so theorem 3.3, let S be a sample space if B1 to Bn are mutually exclusive events such that S is the union of those events, and the probability of each BI is positive for all the i's from 1 to n, then for any event A of S, you have the following two statements. Okay, so proof. So first let's prove A. So for part A, B is a direct consequence of A. So once we prove A, B is going to be proved very easily. But let's look at A. We want to prove the probability of A is equal to the sum of these probabilities. Well, let's go to the whiteboard again. If you look at the Venn diagram, right, and you have, let's say you have your universal sets, U. And so let's say you have a set A here. Okay. Now the B's are mutually exclusive and their union is all of S. So as an example, let's say this is B1. This is B2. And by B1 and B2, by B1 I mean this whole thing in here. By B2 I mean this whole thing in here. And let's make B3 this thing. And then let's make B4 the rest of it. So you see how the entire universal set, the set S actually, the set S, right? The entire sample space, you have B1, B2, B3, and B4. They're all mutually exclusive. They don't overlap, and their union is all of S. For any set A in S, you can see that you can think of A as A, B1, in A and B1, in A and B2, in A and B, in A and B3, and in A and B4, right? So you see how A is a union of the mutually exclusive events AB1, AB2, AB3, and AB4. So A is a union of the mutually exclusive events AB1 union AB2 union AB3 union AB4. And not only is A the union, right, they're mutually exclusive. So the probability of an event A, if the event is a union of mutually exclusive events, that means it's the sum of those events. So the probability of A is equal to the probability of AB1 plus the probability of AB2 B2 plus the probability of A B3 plus the probability of A B4, right? So writing a complete proof is important and probably the most important thing. But what's also pretty important is to be able to visualize the situation and to know and understand why something works, right? And how it works, right? So here we have the probability of A is equal to probability of AB1 plus probability of AB2 plus dot 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 plus probability of ABN. That's just saying that instead of 4 B's, we had n of them. So instead of covering S with 4 mutually exclusive events, we covered it with an arbitrary n number of them. And you can see that you could do the same thing with n B's instead of 4, right? And you would get formula A. So, right, so from this picture, hopefully you can visualize what's happening in the situation, right? Okay, so that's also very important. Not just writing down the equations and getting an algebraic proof maybe of it. So S is equal to B1 union B2 union dot 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 union Bn, right? So since S is the union of those sets, then we can say that first we can say that A is A intersection S, because A is in the entire sample space. But A then is equal to A intersection S, and A is equal then to A intersection, well, what S is, which is the union of these events. But then that's equal to, right? That's equal to A B1 union A B2 union dot 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 union A B N. Okay, and these are mutually exclusive events. These are mutually exclusive events. Since the B's are mutually exclusive, right? The B's are mutually exclusive. These are mutually exclusive events because the B's are mutually exclusive events, right? Since the B's don't overlap, right? Since B1 doesn't overlap with B2, that means AB1, which is a subset of B1, can't overlap with AB2, which is a subset of B2, right? So I'm looking at this. I'm looking at these two events here. If you have one set and you have another set and they're disjoint, they're mutually exclusive events. They don't overlap. Then if you were to take a subset of this set and a subset of that one, this event would be mutually exclusive from that one, right? And so if you have that B1 is mutually exclusive, B1 and B2 are mutually exclusive, then AB1, which is a subset of B1, is mutually exclusive from AB2. I'm not drawing this exactly because the intersection of A, right? I'm not drawing this as a Venn diagram. I'm just illustrating that AB1 is a subset of B1 and AB2 is a subset of B2. And so B1 and B2 are mutually exclusive. That means this set and this set also. So you see that idea, right? The actual Venn diagram, you'd have A, you'd have B, oh, wait. It's B1 and B2. Okay, so you have B1 and B2, they're mutually exclusive. So you have B1 and B2, they're mutually exclusive. And then you have a set A that either overlaps with either or doesn't, right? So AB1 is mutually exclusive from AB2, right? And technically you would put B1 and B2 overlapping and put nothing in the intersection. But I just want to illustrate how these two sets are separate, right? And so these two intersections also have to be separate, okay? Being completely perfect with the picture, there's to illustrate the idea, to really draw, I guess, the Venn diagram. If you had A, B1, and B2, and B1 and B2 are mutually exclusive events, that means there's nothing in their intersection, right? That means there's nothing here and nothing here because B1 and B2 are mutually exclusive. Their intersection is empty. Then A, B1 and AB2 are mutually exclusive events because there's nothing in here. There's nothing here because B1 and B2 are mutually exclusive. So there's nothing in their intersection. That means that AB1 has nothing in this part and only here, and AB2 only has something here and not here. That means that these sets are separate. There's nothing in this intersection because B1 and B2 are disjoint, are mutually exclusive. See that? So I guess this is the perfect picture right here. This is technically, the best way to illustrate it, but these two are the best way to understand the idea. Okay. Let's keep going. So you have that union of mutually exclusive events, but I'm talking about AB1, AB2, and so forth. So then, since they're mutually exclusive, that means that as sets, the probability of A is equal to the probability, since A is equal to this, their probabilities are equal. So probability of A is equal to the probability of that. And then, because those are mutually exclusive, that's equal to the probability of A, B1 plus probability of A, B2 plus ... plus the probability of A, Bn. So see that? So now we just proved that the probability of A is equal to the sum of these probabilities. And so part A is proved. Okay, so it's easy to visualize once you visualize correctly. In part B, the proof of B, well, this is actually much easier than it looks. The probability of A is equal to this probability, right? From part A, you know that this is equal to this. We just proved it right here. But then, just applying an earlier formula, we know that the probability of AB1 is equal to the probability of A given B1 times the probability of B1, plus the probability of AB2 is equal to the probability of A given B2 times the probability of B2. So now we know that the second term is that, plus ... plus the probability of ABN is equal to the probability of A given BN times the probability of BN. And so that's the last one. Okay? And so then that's done. And so now we proved part B, that this is equal to that. And so part B is proved. Okay? Okay, and so that was by parts. This was by theorem 3.2. Right, in theorem 3.2, we said that the probability of A and B is equal to this times this, right? And so you just applied that here. Probability of AB1 is probability of A given B1 times probability of B1, and so on. That's what's happening here. That's if that probability is positive, right? Okay. And we're given that the P of BI's are positive, right? P of B1 is positive, P of B2 is positive, and so forth. And so here the probability of the BI's are positive, and so we have this condition in order to apply that. Okay. So next is theorem 3.4, which is called Bayes' theorem. So if the conditions of theorem 3.3 are satisfied, so let S be a sample space. If B1, B2, and so forth, Bn are mutually exclusive events such that S is the union and P of BI is positive for I, right? Sorry, let me do this. There. I'm going to put this in parentheses. So I'm just going to put it like that. These are the conditions. There we go. Okay, so if the conditions of theorem 3.3 are satisfied, meaning S is a sample space, B1 and Bn are mutually exclusive events, such as S is their union, and the probability of the BIs are positive. So if all that happens, then for any k equal to 1, 2, 3, and up to including n, we have that the probability of B sub k given A is equal to the probability of A given B sub k times the probability of B sub k divided by the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2 plus dot 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 plus probability of A given Bn times the probability of Bn. Okay, this is Bayes' theorem. Let's move this here. So if the conditions of theorem 3.3 are satisfied, S is a sample space, the BIs are mutually exclusive, S is their union, and the probability of the BIs are positive. Then for any k from 1 to n, we have this. Okay. So the proof is just if you take the probability of B sub k, probability of B sub k given A, this is equal to the probability of B sub k A divided by the probability of A, but that's equal to the probability, this is equal to the probability of A given B sub k times the probability of B sub k, right? And then the denominator, the probability of A is equal to the probability of A B1 plus the probability of A B2 plus the probability of A B3 plus dot 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 plus the probability of A Bn, right? The B's cover the union of all the B's is S and they're mutually exclusive. And we said before that then the probability of A is equal to the sum of these probabilities, right? Well, then that means first the numerator is the same. The numerator stays the same. The denominator, the probability of AB1 is the same as the probability of A given B1 times the probability of B1 plus the probability of AB2 is the same as the probability of A given B2 times the probability of B2 plus dot 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 plus the probability of ABN, probability of ABN. Am I just going backwards here? Oh, no, here. Okay, good. Plus the probability of ABN is equal to the probability of A given Bn times the probability of Bn. See that? So this probability is the same as this one. It's the same as this one, right? And so now we have that this is equal to that, and we're done. And we are done. Proof. Okay, so that's the proof of Bayes' theorem. Okay, the next example requires a little bit of writing down, and so next class, we're going to go over an example using Bayes' theorem. So we're going to start class with an example that uses Bayes' theorem. Okay, excuse me. And so reminder, so I announced it last class. Reminder, test 1, right? Test 1 is on July 29th, right? So test 1 is on July 29th and during class, right? Use the same class link for every class. It starts at the beginning of class. Don't be late. You don't want to miss any time in the exam. July 29th during class. July 29th. July 29th. Yep, during class, right? And classes from 10 a.m. to 11:34 a.m. Okay, so the test will be during there. Make sure you have Zoom and everything else. All the instructions I gave last time, keep that in mind. Okay, so we'll stop here. Okay, and so let me. Oh wait, before you go. I'm going to assign homework 3. Okay, so. Oh, actually, no. You know what? I'm going to hold off on that. Okay, no homework 3 yet. Okay, so we're good. Homework 3 has section, I think you can see it on the screen. Homework 3 has section 3.2 in it, and we're not yet done with that. If you want to start, I'm not assigning it yet, but if you want to start studying, you can do this section, you can do this section, and you can do this section, okay? And you can do this section, okay? So I've covered all those sections. There's only one section we haven't gone over yet. And so, okay, so if you want to get ahead on it, okay, so you can start with those, okay? So actually for homework, I'm going to say start working on these red sections. I'm not technically assigning it, so when I do, I'll say it's, it's not due yet, but for homework, I want you to start this homework assignment by working on the red sections, okay? So work on the red sections I circled here, okay? That's your homework. Without a due date, just start working on it. And then next class, I will, announce a due date for it, okay? So get ahead and start working on it. Okay, any questions, anything?
I have a question.
Yeah.
So do you save the whiteboard?
Right, the whiteboard. Thank you for reminding me. Good. Thank you for reminding me about the whiteboard. Okay, so I'm going to save it. Right, so I feel like the whiteboard is helpful. So it's good that I have that saved. Okay, so I saved it. Thank you. Remind me. Okay, so we'll end there. And I'll see all of you tomorrow morning. Bye. Oh, and it's okay. I upload the videos on YouTube. So they're on Blackboard, and a lot of them are on YouTube also. Okay, bye. See you tomorrow morning.